Alright, so the first thing we're going to do is we're going to solve the differential equation 2x double prime plus 12x prime plus 50x equals 0. Initial position is 0, initial velocity is -8. So what's going on here, we've got, say, a 2 kilogram mass with a spring constant 50, damping constant 12. It's set into motion from equilibrium with an initial velocity of 8 meters per second to the left. Okay, so we want to solve for x, we want to figure out what that function is. So in order to do this, we want to solve the characteristic equation 2r squared plus 12r plus 50 equals 0. We can simplify things by dividing everything by 2. Right, divide both sides of the equation by 2. Let me subtract 25 from both sides and then complete the square by adding 9 to both sides. So if I do that, I'd have r plus 3, the whole thing squared, equals -16. So that means r plus 3 would be plus or minus the square root of -16, which is 4i. And so r is -3 plus or minus 4i. So our equation has two complex roots. That means that the system is underdamped here. But let's see what does the solution look like. It looks like e to the -3t times c1 cosine of 4t plus c2 sine of 4t. That's what you do with the a and the b with complex roots. Okay. Now the fact that x of 0 is 0, what does that mean? That means 0 is equal to what happens when you plug in t equals 0, which the right hand side would just become c1. So actually c1 is 0. So that simplifies things a little bit. That means that x of t is really just e to the -3t times c2 sine of 4t. To solve for c2, we need to use the initial velocity, so we have to find the derivative of x of t. That requires the product rule. So let's see, it's the derivative of the first times the second plus the first times the derivative of the second, which would be 4c2 cosine of 4t. So that is the product rule to find x prime. The fact that x prime of 0 was -8, that was the initial condition, yeah. Tells us that -8 would be equal to what happens when I plug in t equals 0 here, which when you plug in t equals 0, the first term just becomes 0. The second term becomes 4c2. Yeah, so this tells us that c2 would be -2. Okay. So our actual solution here is x of t equals, so I just plug in -2 for c2 right here. So it's -2 e to the -3t sine of 4t. That's what our solution looks like. Okay. We're also supposed to do this with the same setup but disconnecting the dash pot. Okay, so if I disconnect the dash pot, that's getting rid of this middle term here. So let's do that over here. So with no dash pot, what is the equation? The equation looks like this: 2x double prime plus 50x equals 0. So my characteristic equation is 2r squared plus 50 equals 0. I could divide both sides by 2. That means r squared would be -25, and so r would be plus or minus 5i. And so our solution here, which I'm going to call u, this is the solution with no damping, u of t would be c1 cosine of 5t plus c2 sine of 5t. And let's see, the fact that the initial position should still be 0, that tells us that again c1 must be 0. So actually u of t is just c2 sine of 5t. To do the second initial condition, we'd have to find the derivative, so u prime would be what? 5 c2 cosine of 5t, and the fact that the initial velocity is -8 means that -8 is equal to 5 c2, so c2 would be -8/5. Okay. So what we actually have is that u of t is -8/5 sine of 5t. So here's what the mass does with no damping. Here's what the mass does with damping. Let's graph those two functions just to compare them. Okay, so I've typed these two functions into my y equals menu. Let's get a window that makes sense. So usually time is positive, so let's go from 0 to 10 on the horizontal axis. And let's see. Here, the biggest that the amplitude would ever get is 2. Here, the amplitude is 8/3, which is almost 3. So let's see. Whoops. Let's see. If I go from -3 to 3 on the vertical axis, I'll be able to see both graphs. Okay, so here, let's go ahead and graph them. And you see there's the graph with the damping. Of course, very small oscillations, because the e to the -3t makes that graph go to 0 really quickly. Oops. And then of course here's the graph with no damping. With no damping, it just literally just bounces back and forth over and over again. What I want to do is zoom in on the very beginning of the graph here. So let's maybe go from just 0 to 1. So I can zoom in on the first second. So the first curve was with the damping, the second curve was without the damping. Notice that they both have initial position 0. They both have a negative initial velocity, right? They both start off going down. That's because they had the same initial conditions. But as time goes on, the e to the -3t really that's the damping effect that causes these the oscillations here to decrease in amplitude, whereas here they don't decrease in amplitude. They just they're just going to keep on going forever.